Morning. I, Peeyush Sharma, Assistant Professor, IIMT College of Science and Technology, presenting uh, data structure known as B-tree. So, without delay, let's start. So, B-tree. What is B-tree? B-tree are balanced search tree designed to work well on disk drives or other direct access secondary storage devices. So, here we can see B-tree is nothing but direct access secondary storage devices. What is secondary devices? Secondary storage devices like hard disk. So the structure of hard disk is such that there are plotters, sectors, secondary storage devices that such that hard disk is divided into plotters, sectors. So to put data on the secondary storage and to retrieve data from the secondary storage, we need a data structure. And for that purpose, we use B tree, right? So B tree is a balanced search tree designed to work well on disk drives for the purpose of whatever if we are writing data or we are retrieving data. B tree is also known as balanced M-Ary tree, having some following properties. So what is M-Ary tree? So we already know about binary tree, right? What is binary tree? The binary tree in which there can be only zero child, one child, maximum zero child, at least zero child, one child, or two child, but not more than two. So that tree will be binary tree, right? In another scenario, we also see ternary tree. So what is ternary tree? Ternary tree in which at most there can be three childs, right? So zero is zero child possible, one child possible, two child possible, and also three child possibilities. So that tree is known as ternary tree. Similarly, for quaternary tree and so on so forth. So we we here see B tree is M-Ary tree. That means there can be at most M child possible, right? So also B tree is also known as M-Ary tree, right? So let us proceed. Having following M-Ary B tree having following properties. What are that? Every node X has following fields, right? Nx. Nx. What is Nx? The number of keys currently stored in node X, right? So before that, for storing data, for the purpose of storing data, what data structure we are using? Array. Either we can use array or data or linked list, right? So B tree is also represented in the form of linked list, right? And every node we can in linked list we already know that every node contains two parts, one is address and another is data. So every node in B tree contain number of keys, right? Which can be represented as nx. Is if n and big brass is 4, that means there are n keys in a node. If n5, then there are 5 keys in a node. If n6, there are 6 node in a node, sorry, 6 keys in a node, right? Now next property is the nx keys themselves store in non-decreasing order, right? Here we already see that B tree is a balanced search tree, right? Balanced search tree, that means keys which we are storing in a particular node that are in the form of non-decreasing order, right? If a node containing four keys, then four keys are stored in non-decreasing order, right? So in the next property we can already see the keys one of x is less than key 2 of x, and is key 2 of x is less than key 3 of the s, and so on. Key nx of the x is the biggest in a particular node. The maximum keys is stored at last, right? And next properties is leaf of x, a boolean value that is true if x is a leaf node and false if x is an internal node, right? If enough if the in a b tree, if uh, uh, a node is a leaf node, right, then its boolean value will be true, and if it is internal node, then its boolean value will be false, right? These are the properties of b tree. Now b tree definition. What is the definition of b tree? So we already know that b tree following b tree as a balance binary search tree. So uh, first property, what is the first definition? Each internal node of x contain n x plus 1 pointers, right? And these pointers are represented as c1x, c2x, c3x, and so on, cnx, and cn plus 1 x. These are childs of node x, right? Leaf node have no children. If nx is a leaf node, then it has no child. So ci field are undefined. Yeah, that means the pointers which are associated with the leaf node are what? Undefined. Third property says the keys key I separate the range of key stored in each subtree. If ki is any key stored in the subtree with node ci, then key k1 should be less than key of 1x, and key 2 should be less than key 2x should be less than. That means see, it follows the b tree property, where in each node we are storing keys in non decreasing order. So this property says like that. This property says this property. Now fourth one is all leaves have the same depth, which is the tree's height, right? In binary search there is not certain that each leaves having same depth, but in b tree each and every path should be of same height, same depth, and that depth is the height of that b tree. Now fifth property says there are lower and upper bound on the number of keys a node can contain, right? So in a b tree there is a node contain keys, right? So in every node there is a bound of the number of keys that can a particular node can hold. That means a node can hold minimum number of keys and maximum number of keys. So these are bound, right? And what are that boundaries? Further we see what are that boundaries. What that means, what are the upper bound and what are the lower bound. These bounds can be expressed in terms of fixed integer t should be greater than or equal to 2, right? That boundary which in upper lower bound and upper bound which we are representing here, it can be bound to this integer t, right? And t should be greater than or equal to 2. T should be not equal to 1 or neither 0. T should be always greater than or equal to 2, and this t is called as minimum degree of B tree. T is the degree, right? And 2 is what? Minimum degree of B tree. Now, every node other than the root must have at least t minus 1 keys, right? If degree is 2, then the root node contain which how many keys? T minus 1. 2 minus 1, that means 1 keys, right? Every internal node other than the root thus has at least t children. If the tree is non-empty, the root must have at least 1 keys. So in further we will see these property, explore these properties. Every node contain at most 2t minus 1 keys. At most, that means maximum keys. Here, t minus 1 is the minimum keys, 2t minus 1 is the maximum keys. Therefore, an internal node can have at most 2 t's children, and we say that a node is full if it is contain exactly 2t minus 1 keys. Here, 2t is children, right? T is degree and 2t is children, but 2t minus 1 is are keys in a node, right? In further ppt we'll explore that. Here we can see that m is root, and m having two children, d one left in the left child, which is a node, contain two keys d and h. In right child contain q, t and x. Similarly, d and h having three children, q, t and x having four children. Here degree is not defined, right? Here degree is not defined. And we also explore that the root can contain only one child. The boundary of B tree, that means upper bound and lower bound, which bound in B tree, should not be imposed on this root node. So clearly we can see a B tree whose keys are component, uh, an internal node X containing X dot n keys, right? Has X dot n plus one children. That means if B tree contain an internal node X, then n is number of keys and n plus 1 is the number of child. All leaves are at the same depth. We can see their depth here, m depth is 0, 1 and 2. All leaves, all paths should be of the same height. We can clearly see here. Now, what are the operation performed in a B tree? Clearly, for every data structure, we are exploring three, that means searching, insertion, and deletion. So, in V-tree, we also inserting a data. How data is inserted in V-tree? So, let us explore. It takes and input a pointer to the root node X of a subtree and a key K to be searched for in that subtree, right? So for searching purpose, what we have, root node, right? And keys which are searching, right? The searching should be on the top level call is thus of the form B tree search t dot root comma k. Key is key which we are searching from where, t dot root, right? So if k is in B tree, then B search tree returns the order pair y comma I, consisting of a node y and an index I such that y dot key of I is equal to k. So while we are searching, if our data is found, that means if k is found, then what B tree return? It will return that particular node and where that key is exist on that particular node, the index where that particular key is stored. Otherwise the procedure returns nil, right? Here is the algorithm. B tree search, we are passing x and k. Here x is the root node and k is key which we are searching. We are initializing I is equal to 0, while I should be less than or equal to x dot n, and k should be greater than x dot key of I, meaning we are iterating I is equal to 1 to till where x dot n, that means number of keys in that particular node, right? If our key is greater than x dot I, then we what will do? We will increment this variable I. And if I is less than x dot n and k is equal to x dot key of I, that means if uh, I is in our boundary and our keys is find at index I, then what will return? X as well as I. Clear? That means node, that particular node where in that node where our keys is stored, and in that node where our key is exist is found, that index should be returned, right? And if not found, then what will return? Nil. So this is the searching algorithm in a B tree. Else what will do? Discrete x dot ci return B tree search x comma ci x dot ci comma k. This is a recursive call. Again and again this will be called, right? So for the searching purpose, what will be the complexity in B tree? Let us analysis on that. As in the tree search procedure for binary search tree, the node encountered during the recursion for a single path downward from the root of the tree, right? In binary search, what we'll do if we are searching a particular keys or particular data, so either we go on the right side of the of our parent, either we are go left side of our parent, right? Here we are applying same procedure, right? So in bit research procedure, there are four access order of H. That is order of what will be the order of H? That will be order of log of n base t, right? Disk blocks, where H is the height of the B tree and n is the number of keys in B tree. Now since x dot n is less than 2t, while loop of the line 2 to 3 takes order of t time, while each node and the CPU time will be order of t of h is equal to order of log n base t multiplied by order of log n base t. What is the meaning of that? The meaning of that is, if we are considering that t is of degree 5, right? So what will be the maximum child lie on that particular on any particular node? 2t minus 1. That means 5 into 2 minus 1. That is 9. In a particular node, there should be 9 keys are possible, right? And what will be the minimum keys? The minimum keys should be t minus 1. That is 5 minus 1. That is 4. So in a particular node, at least there should be 4 keys, and at most there should be 9 keys, right? So in a particular node, if we are searching a key, then we have to search what? Those 9 keys. If we are applying linear search, right? So what will the complexity for the linear search? Order of n, but we are not applying linear search. Why? Because our keys are in sorted order, in non-decreasing order, so we can apply binary search. So that is why the complexity is order of log of n base t. Base t is what? Base t is why? Because it shows the number of uh, sorry, the height of that particular node. So in worst case, if our keys lies on the leaf node, so this log n base t should be multiplied to what? The maximum number of keys in a particular node. That is why order of t of s is equal to order of t into log of n base t. Now another property is Sir, inserting property. For inserting, we have to create a B tree. So already I have told you before that data structure, in data structure, data can be stored in linked list form or array form. So for constructing a B tree, uh, to build a B tree, we first use B tree create to create an empty. Uh, yes, we have to create an empty root node and then call B tree insert. Right? We have to first create a root node. After that, on the basis of keys and degree, we have to insert on that created empty B tree. Right? So B tree insert to add a new keys. Both these procedures use an auxiliary procedure allocate node which allocates one disk space to be used as a new node in order of one time. For example, we are in linked list. We are creating a new node, right? We are allocating a memory for inserting our data. We are creating first a node. After that, we insert on that particular node, data on that particular node, right? So here we are creating on the same procedure. First, we allocate memory to a uh, node, and after that and allocate and for allocating that memory auxiliary memory to that particular node, we will take order of one time. We can assume that a node created by allocate node required no disk read, since there is at no useful information is stored on the disk. For creating a node, we are not uh, using it. We are just creating it. That means we are not inserting data, we are just creating it. So for that procedure, we will take order of n time. Here is the uh, algorithm for creating a B tree. B tree create. First, allocate node to x. After that, the number of nodes allocated to x is firstly 0. Leaf of x is true. Yes. Disk right and root of tree is x. First, we'll create a node X, and after that, we assigned as a root node to that particular node X, which we are creating just now before. And for that purpose, we'll take order of one disk operation and order of one CPU time. And let us now see the procedure of insertion. There is the algorithm of insertion. B-tree insert. R is the root node. R dot n should be maximum 2 minus 1, right? And if r dot n is equal to 2t minus 1, then can we store a particular key in that particular node? Not, because already that node contain a maximum keys. So for that purpose, for inserting new keys, we have to split our node. So s is equal to b tree split root. So here first split, because our node contain maximum number of keys. So first we split, and after splitting it, we will insert our key k to either left side or right side based on the condition. Based on the condition means we are already following the property of binary search tree. So where keys are lies, either left child or right child. So b tree insert non full s k, else b tree insert non full r comma k. Right? Here t is the degree. The maximum child can be possible 2t minus 1, minimum child can be possible t minus 1. So we can already see here the root node, and this root node is splitting a node with t is equal to 4. That means a b tree of degree 4. So how many maximum child can be possible? 2t minus 1, that means 2 into 4 minus 1, that is 7, right? And we are inserting it into a new inserting a this node a new key, right? So what we'll do, for after inserting, we see that it uh, it exceed the boundary of that particular node. So if exceeding the boundary of that particular node, so what we'll do? We split this node. So for a splitting purpose, what we'll do? Since this is non-decreasing order, S goes to its parent and the left keys lies on this S, that is PQR, should form the left node, and the right keys of this uh, particular node S should be of the right child of this uh, keys S, right? So while we are inserting a keys, and if exceeds the boundary of that particular node, so we will, what we'll do, we will split that node. And for splitting purpose, the middle part, the middle key goes to its parent, and the left part of this middle key form the left child, and the right part of this middle key form uh, right node, and lies within this right node, as we can clearly see, right? So after splitting here, the algorithm of splitting this, uh, how this node is splitted. Here is the algorithm, and after splitting it, we will see how keys are inserted. So let us see with an example. Here is the initial tree, right? And we are inserting B into that particular B tree. So what we will the first we will search the position of this B, where this B should be inserted. So we can see that B inserted in this node, and next key is Q, where Q is inserted. Q is insert. First we'll find the position of this Q, and we'll see this. We'll see that this Q lies in this particular node. Why? Q is greater than sorry, Q is greater than C. So in this particular, while we are inserting in this particular node, we clearly see that this boundary exceeds. So what we'll do? We split this particular node. So while we are splitting this particular node, which one goes to its parent? T. T goes to its parent, and QRS makes its right child, and UB makes its left child. Similarly, if we are inserting another key is P, right? So while we are inserting P should be sorry, L. While we are inserting L here, so while inserting L, we can clearly see that this should be lie on this root node. So if we are inserting L to its root node, so we can clearly see root node already contains a maximum number of child. So root node should be also be exploited. So here we can see clearly that after positioning L, root node is also splitted, and uh, the keys which are left to this middle keys, that is P, lie on this left child, and uh, right keys are lies on this right child. But here we have not inserted L yet. So first we will find the position of L in this particular node, and after that we will insert it. And similarly, F is inserted. Also finding the position of F that should be lie in this particular node is also exceeds the number of child, and this is also split into two parts. And this way, in this B tree, we are inserting on any particular keys. And here is the insertion algorithm. So what will the complexity of inserting any particular keys in this node? It should be order of t into log n base t. So this is the exercise for inserting these keys into B node of degree 2. So if degree is 2, so what will the maximum number of keys in a particular node? 2t minus 1, that is 2 into 2 minus 1, that is 3. And what is the maximum number of keys in a particular node? That is 1, right? So here is the exercise for inserting keys into B tree. Thank you.